Or
Yeah.
recording? Okay.
Yeah, I started
So,
recording.
welcome everyone to the 2024 Turing Award winner speaker series of the Georgia Institute of Technology, College of Computing, sponsored by AI2 Incubator. During the course of the semester, 5 Turing Award winners, 1 Nobel laureate in physics, and many other famous computer scientists will be speaking and giving presentations to 2,000 plus RCP students and faculty from the top computer science universities in the world. Thank you very much to our esteemed speaker series advisors, Dr. Svi Galil, Dr. Bjarne Sestrap, for helping to make this initiative a reality. I'm so grateful for your advice and guidance as we plan this tremendous speaker series. Thank you as well to our favorite LinkedIn influencer and sponsor, Aish Sarvazian, for her assistance with helping market the series to her 485,000 plus LinkedIn followers. We simply could not have achieved our stellar attendance numbers without you. I'm extremely excited to announce our speaker, the insanely accomplished computer scientist, Dr. Assaf Schuster. Dr. Schuster is an Israeli entrepreneur and professor of computer science whose work have been published in such journals as Computer Aided Verification and Journal of Systems and Software. Dr. Schuster was born in the Israeli kibbutz Givat Brenner, and he began his academic studies at Hebrew University in 1981 and graduated in 84 with a bachelor's degree in mathematics and computer science. 86, he graduated with a master's degree in computer science. After receiving his degree, he worked as a teacher at the Ort College in Givat Ram, Jerusalem. 1991, he received a doctorate from the Hebrew University of Jerusalem in computer science. His PhD topic dealt with the dynamic configuration of communication networks for parallel computation under the guidance of Dr. Eliyahu Shamir. He then started working at the Technion, and in 2000 he became an associate professor, and in 2007 professor. In 2015 he was named Fellow of the Association of Computing Machinery for his contributions to cloud computing. In 2016, Dr. Schuster co-founded a startup called Cyber of Things, along with Natan and Daniel, and he served as the CTO until the company was sold to Veronit Systems in 2019. Everyone, let's give a massive warm round of applause to Dr. Assaf Schuster. We're really excited for this.
Thank you very much, Axel. Can you hear me? It's
yes.
working. Okay. So I'm not a Turing Award winner yet, but let's see what the future holds. And I was asked to talk today about complex patterns or complex event processing. We sometimes call it CP. And so this is an exciting area of research, and this is what I'm going to do. So let's start with a brief, with an introduction. What is pattern matching in streams? Suppose you have a stream of events coming at you. And by the way, we send the time always from left to right in computer science. So at the beginning, we have A1 and then D1 and then all of these events coming at us. And they come in a stream. And we play a game. We want in this game to identify certain patterns in the stream. So for instance, we want to detect an A, which is followed by a B. And immediately we see this example, and we can also see that example, and so on. And then we say, okay, let's detect a B, a C, and a D, where B, C, and D are the event types. And we do not constrain the particular order on the event types. So we find this match, and we can also ask to detect a C and then an E with no B in between. And of course, this is a match for this pattern. and so on and so forth. We can have a complicated pattern. We can complicate the patterns more and more and play this game forever. However, life is not always a game. And when we look at how real life data looks like, it is kind of different from what we saw in the previous slide. So let's think about a smart city where we have a lot of cameras, and the cameras perform face recognition. These are smart edge devices that perform complicated AI tasks at the edge, and they send us events. They send us events that are simply the result of of the activity as face recognition. And so an event can be a very complex object containing the type of event, which is face recognition, the face ID, which is the identity of the face that was shown in the picture, the picture itself, the confidence level, an explanation why the face is indeed what we see, or the ID, the specific ID is indeed what we see in the picture, and perhaps other options for a solution, and so on and so forth. So we have dozens, if not hundreds, of attributes for each event and for each object that we get from in such a system, and we essentially are looking for patterns in this stream of events that is arriving at us. So what is a complex event processing engine? A complex event processing engine is a software that receives a stream of events. They are sometimes called simple events or primitive events, and it also has a set of patterns that it looks for matches in the stream of events that it receives, and it outputs pattern matches that it finds inside the set of the stream of events that is arriving at it. Okay, so this is an engine, and let's look at an example. Suppose we have security surveillance system, and we want to identify people that arrive at the red room where the cameras that are the purple cameras are situated. And it is allowed to arrive at the red room for the area where the yellow cameras are positioned, but it's not allowed to have somebody coming from the area with the green cameras through the corridor. So the patterns that we are looking for, if we want to have an alert whenever somebody comes from the forbidden area, can be written as follows. It's a sequence of events. First, this face is identified in the main lobby. It's one of the main lobby cameras. Then one of the corridor cameras is identifying the same person. And then the restricted area camera in the red room identifies the same person. Okay, so we have a condition which says that all identifications have the same ID. And in this case, we want to raise an alert. So this is one example. Here's another example of monitoring stock prices. We want to find the sequence of events where the first event is a change in Apple stock price, the second event is a change in Microsoft stock price, and the third event is a change in Google stock price. And the condition says that we have said that the price of Apple stock should be less than the price of Microsoft stock, and the price of Microsoft stock should be less than the price of the Google stock. And all of these events should happen within 10 minutes. So this is a general way of writing a pattern, a series of events or a set of events with conditions in between them and a certain window of time where we look for this complex event to happen. All right, so there are a lot of pattern types in complex event processing. You can talk about disjunctions, conjunctions, sequences that we've seen examples to, negations where you are looking for two events and a certain event type is forbidden to appear between them. Clean closure where we have a certain event type which may reappear an undetermined number of times, and also nested patterns which consists of arbitrary combinations of all of these potential patterns, and the more expressivity we find in the pattern, the better it gets, because people would like to define patterns which are more and more expressive. Of course, the more expressive the pattern, the less, the harder it is to identify the pattern, and the more possibilities we have to scan before we arrive to the conclusion that the pattern that match appears or does not appear in a certain fragment of the string. But this shows you the richness of complex event processing, and why I'm going to claim later on that it's very hard. It's a very hard problem. All right, so where does CEP resides? Within stream processing, we have stream analytics, and later on we are going to talk, if we have time, about stream mining. So CEP is somewhere between stream analytics and stream processing, and depending on the expressivity of the language where patterns are defined. And what about CEP applications? To give you some motivation, so there's an enormous number of domains where CEP comes into play in one way or another. I told you about smart cities, the surveillance systems, which we already mentioned as an example, stock monitoring, online finance, fraud detection, network security monitoring, cybersecurity in general, sensor networks, algorithmic trading, and so on and so forth. There are hundreds of fields where in one way or another CEP is implemented, and all of these areas are multi-billion dollars markets. So CEP is very important, and it's becoming more and more important as times go by, because we become used to do things online, and we become used to do things in real time, and we become used to online processing or real-time processing of events or data streams. Okay, so I gave you some motivation for doing CEP, and let's talk about how CEP is done. These are CEP evaluation mechanisms. You can either use non-deterministic finite automata, NFAs, or evaluation trees, and there were other inventions along the years, but none of these changed dramatically the conclusions and the methods that I'm going to show later in this talk. So let's leave them out of the scope of this talk. But let's talk about non-deterministic finite automata and evaluation trees. So here's a and non-deterministic finite automata, for example, 2. The example that I gave you is a stroke prices, which is going to escort us along the way, along this talk. So the NFA starts with searching for an event of type A. Once we find an event of type A, now we have a partial match. Okay, so the partial match says if you find a B, because the next state of the finite automata is looking for B. Once you find B, you extend the partial match that you got to a partial match which says A and B. Okay, but we also have the partial match which is empty, also waiting for another A, because if another A comes in, it may also be extended by another B. And so we have two partial matches, the empty one and an A. And then we are looking for a C, and you can see below the NFA that we have the conditions in each of the edges. When we take a B, we make sure that the price of A is less than the price of B, and when we take C, we make sure that the price of B is less than the price of C. And how many times, or the rate in which these conditions are fulfilled, is called selectivity of these conditions. And the higher the selectivity, the more partial matches we have. Okay, so let's look at an example how this NFA is running when you have an input stream. The input stream begins with an A. It's a change in the price of I think Apple stock, and the price is 1. Okay, and next event that comes in is a change in Apple stock, and the price is 1, and the next event is another change in Apple stock, and the price is 4. And now a change in the price of the Microsoft stock, and the price is 7. So you can see that that when the events come in, the partial matches are piling up. Okay, because when we met the first change in the price of Apple, we had a zero, an empty partial match, and this empty partial match is escorting us regardless of the number of other partial matches that we have. And then we have 3 other partial matches, which are changes in the prices of Apple stock. And now we have new partial matches that are defined by adding B, which the NFA is looking for, to the initial partial matches that we had. So when we meet B1, for instance, it's extending the partial matches A1, A2, and 3. And so we have another 3 partial matches. And when we meet B2, it's again extending 3 partial matches, and is same for B3. And only when we get to C, we start to evaluate the conditions. And when we start to evaluate the conditions, we see that in fact B1 and B2 do not meet the conditions that we had, and so we remove these partial matches, and only B3 is possible, and we get 3 outputs, which is indeed what the NFA was looking for. So this is basically how it works. And what you can immediately see here is that there is a problem. And the problem is the accumulation of an exponential number of partial matches and the handling of this exponential number of partial matches. Because in each arriving event, the engine should go through all the partial matches and look for extensions using this partial event, so using this newly arriving event. And for trees, it's the same. Here's a tree that is evaluating the same example that we have. We want to look for the same pattern, and let's look at how this tree is evaluated with the same example of input stream of events. So initially we have the empty partial match, and now we have one partial match with a change in the stock price of Apple, and so on and so forth. And you can see that the partial matches are accumulated in the same ways as they were accumulated when we worked with the NFA. And only when we get to C, we are able to rule out these intermediate partial matches and focus on the result. So the basic problem that we have exponential number of partial matches that we need to store and we need to maintain is still there. Okay, so until now I talked to you about the mechanism that CEP is using and the motivation for CEP. And let's talk a little bit about the challenges of CEP. What do people want to do and what do they ask when they use CEP engines? So here are a few examples. These are only examples. So you may ask, why is my CEP so slow? Because it maintains so many partial matches. Why is my CEP eats more RAM than Chrome? Because it maintains so many partial matches. And then you can ask, I want to predict future events before they occur. Oh, this is something new. You want to look at the history and predict the future using a CEP engine. And you might want to detect patterns, but you might not have any. So you want the CEP engine to help you come up with interesting patterns. And you want to run the system in the cloud. Are there any showstoppers to running a CEP engine in the cloud? So essentially, you can divide the challenges to performance challenges and functionality challenges. Okay, and there are many, many more of them. You can ask if suppose the events that arrive from a distributed system and the time stamps on them are not representative. How will the CEP engine proceed to work? And you can ask, suppose I want to find instances or matches to patterns, even if they do not exactly match, so approximate matching. And you can ask, suppose the events are uncertain. It is not certain that a specific event happened or not. How can you still detect matches with high confidence level? And you would like to search for thousands of patterns, not just a single pattern. And you can say that some patterns are more important than other patterns, perhaps return their matches faster than the other, and so on and so forth. There are infinitely many questions that people are interested to answer when talking about CEP engine, and only very small part of them is already answered and already has a satisfying solution. The basic problem is that the CEP performance is a nightmare. To detect all occurrences of a given pattern, you need there's a combinatorial explosion of the possibilities that you need to consider. The number of partial meshes that I already showed you. So consider the following example. Suppose you're looking for a sequence ABCD, and suppose you have 1,000 A's, 1,000 B's, and then 1,000 C's. So already when you get to the first D, you have 1 billion partial matches of A's times B's times C's, which shows you where the nightmare comes from. And this problem becomes harder with time essentially because of two basic or foundational trends. The first trend is that patterns used to be defined by humans. And when a human defines a pattern, it defines a pattern of 3, 4, 8 primitive events, but not really more than 12, let's say. Okay, it's too cumbersome to understand a pattern which is too long. However, recently people started using AI in order to generate patterns, and if we have time, I'm going to show you a few things about that later on. And so patterns become more and more sophisticated and more and more and longer with time. So it's becoming a real showstopper, the fact that patterns are very, very complicated and very, very long. The second problem, the second trend that we are talking about is that streams were used to be consisting of human created events. But recently, we are talking about streams that are created, that are generated by sensors, by sensor clusters, and by machine-to-machine interaction. And these streams become more and more massive. You start to need to process these streams in the rate of dozens of thousands or hundreds of thousands events per second. And so the whole thing does not really show to be converging. The area is showing high challenges of performance and high challenges of expressivity and all other questions that we wanted to answer. All right, so let me talk a little bit about directions of research in these to face these challenges. And so let's start with data-aware CP. So I told you that we have two evaluation mechanisms, the tree and the NFA. Let's talk about the tree here. You can see that there's an exponential number of different trees for a system that would like to detect a pattern in a stream that has n event types. And here, every color actually defines an event type. And you can see that there are many different trees that you can use. And choosing the best tree is in fact has high influence on the performance of the results. And so the idea is to use statistical data properties to select the best plan. When I talk about statistical data properties, I mean the rate of incoming event types and also the selectivity of the conditions and so forth. So let me give you the example on our running example here. So we talked about this example of stock prices, and we said this is the NFAs that represent this that can be used in order to evaluate this query. But now it might be advantageous to change the order of the events in this NFA. Suppose we want to check for C first, and only then for A and for B. Okay, so we look for C, then we look for A, and then we look for B. It is possible. There is no problem. The only problem is that we need to, so we need to check for the conditions, for both conditions at the end when we take B, because without B we cannot evaluate these conditions, but that's okay, we can do that. And it gives us a very high advantage when C has a very high rate of arrival, a very low rate of arrival, sorry. Because when C has very low rate of arrival, this NFA will not start accumulating partial matches until it meets the first C. If C is rarely arriving, then we'll have much less partial matches. And in the same way, we can also change the evaluation order and take B first. Look first for B. Maybe B is rarely arriving, and so we want to look for it first, and only then, to look for B. Where am I? Okay, only then to look for C, and only then to look for A. And in general, we have 6 possibilities for different orders, and we can use all of them. We will see in a second how, but intuitively, you already understand that you take the rarest events, the rarest event types, and you look for them first, and then you have much less partial matches to worry about. How is this going to run at the engine? So we have an input buffer which is going to store the events which we meet but we do not look for in the NFA. So for instance, if we are looking for, the order is now CBA, so we are looking first for a C. Until we find the C, we just store all events in the input buffer. Of course, this requires some intermediate storage and space, but the space is linear in the input, and the maximum of the space that we will need is the maximum number of events that arrive within a window. For instance, the window here is 10 minutes. Okay, so it's not exponential anymore. Once we arrive at C, we start accumulating partial matches, but look at the input buffer. It is now very easy to rule out the 2 first Bs, which do not meet the conditions, to choose the third B and to have all results immediately output with very little partial matches to worry about. Okay, so data aware and statistics aware evaluation of CEP turned out to be a big hit. You know, it's a very simple idea, but it's working great in real life. If you ask me about the worst case scenario is going to be very bad with this, or it's not going to help at all, because everybody are going to come at the same rate, or the rate is going to reverse immediately when we start a certain order. But you know, in real life, it really works great, and it became a hit. But the question is, okay, so we know that we want to work this way, but how do we determine the best evaluation plane at any point in time? Okay, so there are multiple parameters that we need to consider: the event arrival rates, the predicate selectivities, the predicate cost, and there are multiple optimization goals or multiple objectives The first objective would always be the throughput, but sometimes for time-critical systems, the latency becomes an important objective, and the space needed for the engine is also important. So the question is, we know the selectivities, we know all the parameters, but still determining the best evaluation plan is a hard problem. So instead of starting to look for algorithms to determine the best evaluation plan, we went in a different direction. So a traditional problem in computer science is joint order estimation for tables. And it is a well-known problem in databases from the 80s. Okay, so for 40-something years by now. It's extensively studied, dozens and dozens of great algorithms that were published and approaches and various approaches. And the question is, can these algorithms be used for to generate CEP plans? The problem for joint order estimation in databases is as follows. You have several tables, say U, T, R, and S, and you want to know which order to evaluate these tables so that the space is minimal, so that the number of operations that you perform is minimal, and so on and so forth. Okay, so N relation on M attributes, we want to do this we want to do this optimally. And you can see that, you can already see that there's a tree of possibilities, and the number of possible solutions for the tree is very high on the one hand, and on the other hand, there's already exists a plethora of solutions that people have already published. So can these algorithms be used for CEP plan generation? And the answer is yes, for conjunctive patterns. So patterns that rely only for end, on the end, so only for conjunctive CEP plan generation, we can have a reduction that reduce it to join queries to compute the best possible tree for join queries. Okay, so we get because we have this reduction, we get that these problems are actually the same. And if you also had a reduction from non-conjunctive CEP plan generation to conjunctive CEP plan generation, you get that the joint plan generation problem solves, if you can find me a good algorithm for it, it solves also the CEP problem. And that was a big thing, because immediately we got an amazing number of tools, of great tools that can be used in order to solve the CEP problem. We got the greedy algorithms and hybrid algorithms and mixed integer programming and genetic algorithms, graph theory based and local search and so on and so forth. All the algorithms that people created in 40-something years of research in the database domain immediately applied to CEP evaluation plan. And that was really fantastic. However, we also asked, how do we apply this CEP, this data-aware CEP in practice? And will these data-aware methods work in real-life scenario? And the answer is, you need to know the arrival rates of all the events. You need to know the selectivities. You need to know the selectivities and arrival rates are usually subject to frequent changes. So we need to have a scheme that will be able to adapt very quickly and with not a lot of overhead. So how does a CP engine, which is adaptive to data statistics, looks like? We have the statistic collector. It collects all incoming events and computes the event arrival rates, the predicate selectivity, the data distribution, and so forth. We also have the evaluation mechanism, which given an evaluation data structure, also handles the pattern detection. It accepts the evaluation plans from the optimizer, and it computes the matches with the input stream. And then we have the optimizer, which accepts data statistics from the collector. It decides whether reoptimization is required, and if needed, it creates a new plan. And the question that we have in mind is, how do we decide whether reoptimization is required? So common strategies are periodically reoptimize the evaluation plan based on the new statistics. However, if you talk about fixed period, you run into the overhead latency trade-off, because if the period is too high, then you are late to reoptimize your system, and you're late on average by half the period. And if the period is too small, then it inflicts a very high overhead, because optimization is a heavy operation. And another approach is to monitor all statistic value against a predefined threshold, which turned out to be very inaccurate, because you do not know the threshold and you need to compute it and so on. And it's very unstable, because if you undershoot or overshoot, and you may find yourself juggling between them. And the question is, can we do better than that? So here's one method, which I'm going to show you only by means of an example, but I'm sure you'll understand it. So suppose you have the rate of event type A 100, and the rate of event type B 50, and the rate of event type C 10. And we have this, we are looking for the sequence A, B, and C within 10 minutes. So of course, according to the logic that we discussed before in this talk, we will first look for C, because it will create the least number of partial matches. But this can be done by applying a simple sorting algorithm, and you look for the lowest rate and you look for it first, and now you look for the second rate and you look for it second, and then for the highest rate you look third. And of course, you can monitor the three conditions, these three invariants, to make sure that the statistics does not change. And of course, the highest one, the third one, is not required. It's enough to monitor two of them, because the third one is a consequence of the first two. All right, but now what happens if the rate of A changes all of a sudden? Okay, so if the rate changes and you're monitoring the invariance, you'll notice that this invariant is still true, but that invariant changed. Once this invariant changes, now you need to recalculate the evaluation plan and find out a new one. Okay, and you change your evaluation plan according to the rates of the different event types, and according to the logics that we described. So This looks like a very simple mechanism, but it generalizes great and it works great. It is computationally cheap. It avoids false positives altogether. We could prove that. It drastically reduces the number of false negatives. It can be applied on any deterministic plan generation algorithm utilizing step-by-step building approach, a very general step-by-step building approach. Although the example I showed you is simplistic, it generalizes to any evaluation plan. All right, so we also can talk about multi-pattern complex event processing. Usually when you talk about a CEP engine, it does not look for a single pattern, but it looks for thousands of different patterns. And some of these patterns may share similar sub-expressions, so this can help us optimize the operation of the engine. And independent evaluation of each pattern is unrealistic, so we are trying to maximize this sharing sub-patterns. So for instance, here you saw two patterns, and all of a sudden the prefix of both is the same, so they can share the evaluation of the first two states. And also here you can see subtrees which can be shared. They are the same, so we can join together the evaluation of this subtree. And if we look at data-aware sharing, okay, we start like that. We see that the prefix is the same, and also the yellow states are the same. So maybe we can change the change the order of both patterns, and now we have the yellow in the center of the prefix, and now the prefix the prefix that we can share is longer, so we have gained. However, we run into a trade-off because sometimes a better individual performance of pattern detection, some change in the order gives you better individual performance of pattern detection, but individually it provides it's worse in terms of several of the patterns that need to be evaluated. So there's a trade-off here. The amount of sharing may grow, and the individual performance of specific patterns can be ruined. So how are we going to solve this? I'm not going to get into the details, just saying that we build very large trees of states, of global states of the NFAs, and we move from one state to another by a single switch in the order of evaluation. And we build large trees and multi-trees, and so then they are pretty complex, so I'm not going to get into the specific construction, but I would only say that now that we have these trees, we can search them using local search. Okay, there's a hyper-exponential number of possible solutions, of course, with those trees. And what we do is apply local search. We start with some initial solution, and then we move through, we search through locally through the different solutions by each time applying a single change in the evaluation tree and looking for places where we monotonically improve the solution. Of course, we need a cost model to evaluate at each solution the cost, but we can do that, and this is another thing that we could do. All right, so you may ask also, what about parallel evaluation? can parallel evaluation help us out from the fact that it's very hard to do complex event processing. So people offer to do data parallelism, where they split the data between different different workers, and each of the workers is working on another part of the data. However, there also needs to be a merger after all of them, which needs to synchronize what they do, and it's it's suboptimal. And other people suggested state parallelism, where every worker is in charge of adding another event to the partial matches that we already have, and so the maintenance of partial matches is distributed across all the workers. This is also not ideal. It turned out that we do a lot of extra work here, and we suggested hybrid parallelism, which takes both approaches and take the best of both worlds. And hybrid parallelism turned out to be a hit, again, because if you look at the maximal memory usage of each of the cores that are involved in the parallel execution, you can see that with 24 cores, for instance, the amount of data that you need to process relative to the state-based, for instance, solution is 1.5 orders of magnitude less. And so why is it so nice? Why is it so good? Because when you reduce the amount of data that you need to process at each core by 1.5 orders, then you move upwards in the memory hierarchy. So you can use caches which are smaller and faster. And as you can see here, the 1.5 improvement in the usage of memory in fact manifested itself with more than 3 orders of magnitude in the relative throughput over the sequential approach. Okay, so the equivalence to speed up, or the amount of data that we are able to process with 24 cores is more than 3 orders of magnitude more than the amount of data that we are able to process with 1 core. Which brings us the question, how come? I mean, we only applied 24 cores, so we should be able to do only 24 times faster. And again, the answer is that when you reduce the amount of memory, you get superlinear speedup. And the superlinear speedup comes from the fact that you need less memory, and so you work with much faster levels of the memory hierarchy, and you get superlinear improvement. In this case, more than 3 orders of magnitude. And the same holds for the latency. You can see that the latency improves by 1 order of magnitude when you move from 10 cores to 24 cores. Maybe 2 orders of magnitude latency improvement from the single core approach, from the non-parallelized approach. Okay, so I think I talked already for 45 minutes, so maybe we can stop here. I have a lot of slides, but that's maybe another talk. Maybe I'll scan them very fast for you. Of course, many people ask, can we throw in a deep neural network and solve the whole thing and be done? So the answer is maybe. Okay, so the answer is yes and no. The answer is no, because CEP patterns are highly convoluted, and you need to consider all of these matches in order to understand whether you have all of the possible arrangements in order to understand whether you have a match or not. This is not something that neural networks is good at. On the one hand, okay, neural networks, they are good as functional approximators. Grouping the inputs into subsets is extremely challenging for them, okay, and they do not know how to do that. And moreover, I already showed you that CEP evaluation is equivalent, or is at least as hard as NP complete problem, which is the join order problem from databases, and the join order problem for databases is known to be NP complete, NP hard. And we know that deep neural networks are not very good in tackling NP hard problem. In fact, we proved that neural networks are not efficient when they try to solve NP complete problem. So what can we do? Okay, we can try to put a neural network filter that will look at the input stream. We need to rearrange the input stream a little bit into windows and so on, but that's okay. We now take this rearranged input and input it to the neural network, and the neural network is going to filter out events that it knows have very low chance of participating in resulting matches. Okay, so if we have an input stream and most of the events are deleted by the filter neural networks, then we only have a partial substream as the output, and so the filtered substream is going to be inputted to a CEP engine, which will have much easier life in order to find out matches, whether matches are there or not. And this is one approach, and we were able to work with it and eventually get nice results. For example, if you look at the results, for example, we were able to lower the latency. If you look at this example, so we were able to get throughput gains of 100 to 1,000 events per second that we can process with a recall of 80 to 100%. A recall is the number of matches that are not lost. So out of the matches that we are looking for, how many matches we found? And actually, most of the domains that we looked at, we found close to 100% recall. And the latency is going down dramatically. You can see this example, for instance, with arrival rate of 500 events per second, and you're looking at the percentile latency for the percentage of matches. Okay, so if you, for instance, have a percentage of matches, 50% of the matches, they are detected with latency of 1250 seconds with the CEP engine, whereas in the blue solution that is consisting of a neural network, the latency drops down to almost a zero. And if you look at a case where you have 1,000 events per second coming in, then again you see that the latency is very low relative to the other solutions, but on the 80th percentile, it goes up, and it's not 0 until the 80th percentile. So I could go into these results deeper and deeper for another hour or two. But I guess let me stop here and only say that CP challenges are still there. We are looking at how to apply new tools that computer science provides us with. For instance, deep neural networks to this to computing with event processing, and there's a lot to do, and it's very interesting. So thank you very much for inviting me.
Yasher Koach, Dr. Assaf Schuster, thank you so much for your extremely insightful presentation. And then, so can I get a virtual round of applause from our audience members? Virtual applause. There we go, Clyde.
Thank you very much.
What questions do the audience members have? I know Sanjaiva Prasad, you had a question recently. Yeah, Clyde. Let's see.
I can't
Sanjaiva,
see. Okay.
Sanjaiva, if you want to put your question in the chat again, or you're not going to get your question answered, I guess. So, yeah, we'll have like 30 more seconds for anyone with a question. If not, if no one has a question, they ask, how do database results like Chandala, Merlin, or Fagin help? I don't know if you can see that, Assaf.
No, I cannot.
Okay,
Maybe you
see it.
can.
How do let me send you an email. Yes.
Oh, maybe, yeah, now I can see it.
Oh, you can see it.
How do database results like Chandra Merlin or Fagging cyclicity help? Frankly, I'm not able to answer that because I'm not aware of these. I'm not, did not look, did not think about them. So
cool. Yeah. So, Dr. Schuster, thank you so much for coming. I'll be following up with you shortly to inquire where we can send you Godiva chocolates as a thank you for your taking the time to do this. I want to say that I hearing what's going on in Israel is making me very sad, and as a Jewish American, you guys mean a lot to me, and I'd love to stay in touch and extend our deep appreciation for your time and willingness to speak with us. Thanks as well to everyone in the audience for your attendance, and we'll see everyone next week. We're going to have Dr. Jack Dangara, who won the Turing Award, I think in maybe 2021. So yeah.
okay, thank you so much.
Absolutely. Yeah.
For
Yeah, let's stay in touch, and we'll be following up with you on where we can send those chocolates.
Sure. Thanks a lot.
Of course.
I'm already hungry thinking about it.
Yep. Okay. Bye, everyone.
Bye.
Lahitro.
Dito.